Now I'm really going to start talking about orbits. So, what I love about orbits is we can apply Newton's second law, which is F net equals ma, and we can also apply Newton's law of gravity, which I talked about early in the semester when I was explaining to you what little g meant. And if you recall, Newton's law of gravity tells you what the force is between two objects of a certain mass, and this is the gravitational force. It's very small for most small objects, but when you start putting a large object in there, often the capital G is written first, but this is the equation. Basically says if you have two objects, one object mass 1, another object mass 2, separated by some distance from their centers, r, that's the separation between the centers of the two objects, that the force of the attractive force between them is going to be equal to the product of the two masses divided by the distance between them squared times this constant g. And this g is known as the gravitational constant, and it's equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. All right, we did talk about this a while ago. You may or may not remember it. But we're going to use it in thinking about gravity. So we have two objects. Typically, when we're talking about gravity, one object is going to be bigger than the other when they go into orbit, but that's not always going to be the case. But for the examples we're going to do, that is going to be the case generally, that one object is significantly larger than the other one. And when that's the case, we're interested in the smaller one circling around the larger one. That's called an orbit. The moon goes around the Earth like that, for instance. The Earth goes around the sun, and so on. Or satellites we launch go around the Earth. They get put into orbit around the Earth. We're going to assume that the orbits are perfectly circular for our discussion. In general, orbits are not circular. They can be elliptical. They can even be parabolas, meaning they'll only go around once, then they'll go off forever. But we're going to be talking about the case where it's a perfect circle, which is rare. But it's simple for us to deal with that, and it works for estimating a lot of the quantities we'll be interested in looking at. The moon is in an elliptical orbit around the Earth, and as a matter of fact, if any of you saw the moon Tuesday night, April 7th, it was its largest for the year, a very big full moon. The reason is because the moon happened to be full when it's closest to the Earth this time. Other times, the full moon can be further away. It's not as bright. It's not as big. So the moon's orbit around the Earth is elliptical. We're going to assume it's circular without too much error, but it does make a small difference in terms of how close or how far away the object is from the other object. All right, so I'm going to use this equation for gravity here. I'm going to use that along with this equation, which is Newton's second law that you've been seeing all semester, knowing that when an object is in a perfect circular orbit where its speed stays the same, that its speed is going to be equal to v squared over r, where r is the separation between the two objects. It's the same r that we have here. All right, so I'm going to put all this together. Now I'm going to imagine that we're the orbiting object here, and I'm going to say, well, what force is this object experiencing? Well, it's experiencing this force, Fg. That's the only force it's experiencing. So I can put that in my equation and say, okay, m1 times m2 over r squared times g is equal to, in this case, equals m2 times a. So here m2 is the smaller mass, m1 is the larger mass. So what we're going to see is that the m2's cancel each other out. So what we're going to be left with is that m1 times g divided by r squared is equal to v squared over r, which I'll substitute the a for v squared over r over here. So I'll rewrite this equation. Now, once I cancel out the m2's, I'll have m1, which is the mass of the center object, times g divided by r squared is equal to v squared over r. All right, simplify it just one step further. I'll simplify it and then I'll go to the next page. I could say G times M, I'll just call it M, that's the mass of the object in the center, call that mass M, divided by R equals V squared. So what I did is I multiplied both sides by R. So I canceled the R on the right side and canceled one of the R's down in the numerator here. I'm sorry, the denominator here. So I have GM over R is equal to V squared. I'm going to go to the next page and I'll rewrite that equation because it's a little hard to see. What I ended up with was this. It said G times M divided by R is equal to V squared. So this is actually interesting. Let me explain what this equation is telling us. R is the separation between two objects. This object is mass M2, this object is mass M. And we don't even care about this mass of this object here. It can be anything, doesn't matter. That matters. G is a constant, that's the 6.67 times 10 to the minus 11. R is the separation between them, as I said. And V squared is the speed of this object squared. So it has to be, it's moving with a speed V. So this could tell us, if we knew how fast it's moving, we could know what radius it's in orbit around the object. If we knew the radius at which it's in orbit around the object, we could figure out how fast it's moving. Kind of interesting. This is an orbital equation. Now, while it's interesting and useful and we can use it, what we find is that it's often difficult to measure the speed of an object in space. It's not the first thing we're going to be able to determine. But what we're often able to determine is how long does it take this object to go around this other object. That's a little bit easier to figure out. We know the moon, for instance, revolves around the Earth in 27.3 days. So that's something we can find. And if we know R, that's the separation between them, then we can relate V to both R and the period. That's how long it takes for one object to go around the other object. So I'm going to just write this here. I'm going to just say here T is the period. It's called the period of an object. It's how long it takes to do one big loop around another object. So it's a time. It could be seconds, it could be days, some unit like that. V is the speed of the object. And if you wanted to know the speed of an object in terms of how fast it's moving, but it's going around another object, it's going around in a circumference, you take that circumference, which is a distance, and you divide it by the period. The circumference is equal to 2 pi r. So if you take 2 pi r and divide it by the period, then you have the speed. So what I can do then is I can plug this v in to this equation here. And let's see what I get. I have g times m divided by little r is equal to 2 pi r over t, that whole thing squared. So all I did is I replaced this v with this expression 2 pi r over t. Now let me multiply everything out and see where I'm at. I have g times m divided by little r is equal to 4 times pi squared times r squared divided by t. I can simplify this by multiplying both sides by r. So this is going to be equal to, I'll go to the next page and pause and do it yourself. That's good practice. Just algebra at this point. But on the left, I'll have capital G times m. On the right, I'll have 4 times pi squared times r cubed, this should be t squared, divided by t squared. All right, go to the next page and write that down. G times m equals 4 times pi squared times r cubed divided by t squared. And sometimes what we do is we bring the 4 pi squared over here. So you'll see this written a number of ways. You might see it like this, g times m divided by 4 pi squared is equal to r cubed over t squared. There's a lot of ways you can write it that are all equivalent. Sometimes you'll solve for one of these terms. You might solve for r cubed. Say r cubed equals t squared times g times m divided by 4 pi squared, and then you'll take the cube root of both sides, and you'll see how r, the distance between the two objects, relates to the period and the mass of the center object. Or you might solve this for t, and I should say, okay, this is equal to r. Or you might solve this for t, and you'd say, okay, I'll rewrite the original equation. Gm divided by 4 pi squared is equal to r cubed over t squared. Solve this for t. I can invert both sides. I can say, okay, 4 pi squared divided by g times m is equal to t squared divided by r cubed. So then I multiply both sides by r cubed, and I get t squared equals 4 pi squared r cubed divided by g times m. Take the square root of both sides, and I get t equals square root of 4 pi squared r cubed divided by gm. And I imagine you could, if you wanted to, you could simplify this and say this is equal to 2 times pi times the square root of r cubed divided by gm. So if you knew the distance between one object that's being an orbit around another object, and you knew the mass of the center, the larger object, you could solve for the period this way. So here's a couple of equations that you might find useful, and we'll be doing some examples of these in the next video.